Okay, this video is all about junction capacitance in transistors and little diodes, and the quite large effect they can have on systems such as dual piece. So what we're going to be testing here is to see if we can get this LED here to light purely from the junction capacitance of our little diode here, which is a 1N4007, 1000 volt rating and at 1 amp. So of course when we use our signal generator we won't be coming anywhere near that 1000 volts, probably more like about 6 volts of positive voltage on this side, and our negative will be on this side. It will be a sine or a square wave, offset square wave with a very low duty cycle on the reverse side of the diode, simply so we can see if we can get this LED here to light off the PN junction capacitance of that tiny little diode there. So that's in relation to our transistor. It's been said that the tiny capacitance value between each junction is diddly squat to worry about, and basically not going to show up on anything you build. And like I said, this is in regards to dual piece, and why we're getting a reverse current flow from the base. So the first thing we want to do is find the breakdown voltage for this transistor, which is a 2N3055, and to do that we're using this simple little circuit here. I'm going to apply positive voltage to the emitter, and our ground will be on the back side of the 6.7 k ohm resistor, so if we don't send too much current the wrong way once we hit that breakdown voltage. And I also have my power supply limited to 50 milliamps, which is as low as it'll go. So we have our multimeter across a base emitter junction, with the positive of the multimeter and the positive of our power input is on the emitter side, and the ground is on the back side of this 6.7 k ohm resistor, which is on the base, which is where the negative side of our meter is hooked. So what we'll see is, as we raise the voltage on our power supply here, we should see that voltage across our meter until such time as we reach the breakdown voltage of the emitter base junction, and at which time, because of the high value resistance we got here and the very limited current that can flow through it, we'll see our power supply voltage go up, but our multimeter voltage will stay the same, and that will be showing us what the breakdown voltage is. And the reason we need to know that is so we don't exceed that voltage when we're doing our junction capacitance test, which will be this circuit here. We have an LED on the base of the transistor, so as current can't flow into the base and out of the emitter, we're going to be using the junction capacitance to carry that positive current through the LED in the right direction and see how bright we can get that LED. I'm not going to get into this bullshit question about current not being able to travel through a capacitor. It does and it doesn't, but nonetheless, like any other capacitor, we will see the forward current into our LED until such time as that capacitor is charged, and there is no potential difference between the two. Anyway, so We're going to do our little breakdown voltage test now. We can pretty safely say we can start at 5 volts. Some 2N3055 brands about 8.59 volts. I happen to know this one is going to be up close to around 15, this particular brand, which I do have one of. If you can read that in the camera, not sure. Oh, and it's downside up. There you go. So these ones have a fairly high breakdown voltage between emitter and base. So we'll just check that now. Okay, so our supply is now delivering our current, or becoming our voltage source, and we can see that we have the 5 volts on our multimeter. So to save it being long and boring, we'll go up to 10 volts. And we still have our 10 volts. Go to 13. We still indeed have our 13. We'll go to 14 volts. We still have our 14. We'll go to 15 volts. Still have our 15, and we'll now go to 16 volts, and now you see we're slightly below 15. We have just hit our breakdown voltage. We'll try 15.2, 15.06, so 15 volts for this transistor. Exactly, that is our breakdown voltage of the emitter base junction. So now we know that, I'll write that down there, and when we do our capacitance test across that emitter base junction, we will keep it below that 15 volts, so as we know current is not being passed due to breakdown voltage of the emitter base junction. So I'll go ahead and we'll get that part set up. We'll do this one first. We know that's a 1000 volt diode. My power supply is not going to go anywhere near 1000 volts, and we'll be well below the voltage. So first we'll do the test across here, see if we can get our little LED to light up purely from the very minute amount of capacitance in the PN junction of that teeny weeny little diode. Back soon. Alright, so what this little test here is about is some of us have a dual piece, and we can place an LED across that 1K resistor that's in the dual thief either way, and it will light either way, which doesn't make much sense because current isn't supposed to flow back out of the base when the transistor switches off. But if you have even a 2-to-1 turn ratio, where you may have 10 turns on L1, 20 turns on L2, you will get a current flowing back out of the base due to the emitter base junction capacitance, millicapacitance I think they call it. And that's what we're looking into now. But before we jump in to our large steel can transistor, we want to see just how much of a small amount of capacitance it takes to light an LED. And this tiny little diode here, I can assure you, does not have a whole lot of junction capacitance between the PN junction. But is it enough to light the LED? And also keeping in mind we have it across a 1K ohm resistor, which is present in our dual piece circuit, the standard dual piece circuit. So we're going to give it a go. Now my dual piece, one of them, runs at about 15.3 kilohertz, so that's what I've set the frequency at. Our little forward spike is only going to be 3%, and wound it right down to make this test as hard as possible for the LED to light via that tiny amount of junction capacitance in the little diode there. But that's what we're going to do. Of course, the off time or the off period for your dual feeds will be much more than that, probably around 30 to 40%, and if you start tuning them, 50 to 60% off time is good. So that's what we're going to do. The positive side, or that little 3% forward spike, is going to be travelling the wrong way through the diode via the junction capacitance, and then through our LED. So the diode is in the wrong direction for current to flow through it, but the LED is in the correct direction. And of course, in this case here we have a 12 volt peak to peak, and we have no offset. So channel 2 on the scope will be showing us the actual signal going across this little circuit, which is our blue channel that is hooked across all of the circuit. Our yellow trace is going to be showing us what is across our little LED and resistor. So the little spike on the top side of the 0 volt line, so this trace here, the little spike, that 3% you see, is what the LED will be running on, and the bottom half, which is the other 97%, would be replicating your on time for the transistor in your dual feed circuit. The bottom trace will just show you basically the same, only a higher voltage value. Of course, we're not going to get that voltage value the same on the yellow trace across the LED, because we're going to get a voltage drop across that diode, and also across the resistor, and blah blah blah. The LED itself will clamp the voltage at a certain level. So what's going to happen? Are we going to switch it on and see the LED come on, or what, from that minute amount of junction capacitance in that little diode? Let's give it a try. Okay, so there is our signal. This is what is being sent from our signal generator. You can see I've dropped the blue trace down one division from 0 to get the two traces apart and out of each other, so our 0 volt line is there. You can see at 5 volts per division we have our 6 volt peak and 6 volt on the back side during our off time of the LED. Across the LED resistor you can see our maximum voltage is 4.2, 4.4, and our minimum voltage is 4.8, which is what is expected. And have a look at that little LED go. Unbelievable. Now we may be adding a little bit of capacitance with our scope probes and that, so we're going to remove them now and get them off the job altogether. So that cannot be the culprit. And as you can see, those scope probes and leads and that added bugger all to the system. Actually that LED's actually got brighter by the look of it. And my camera's gone out of focus. And there you go. So that LED is running that bright from that very small minute amount of capacitance that's in that tiny little diode. So diodes are supposed to stop current flowing in the wrong direction. In this case it's doing pretty good at allowing current to flow in the wrong direction, and I'm not going to get into current flows across capacitors. Obviously there is current flowing through the LED and the resistor, otherwise the bloody thing wouldn't be going. But anyway, there you go. So what do you suppose is going to happen when we do the same sort of thing on this big steel junction transistor? Well, I'll go ahead, hook it all up, we'll come back and we'll have a squizzy. Okay, so the first thing we've got to know is that the LEDs are around the right way, and it can only accept positive current flow on this side going in. As you can see, we're hooked to the power supply, we have no LED running. We'll now put the positive on the other side of the LED, like so, and the LED is going. So you can see we have it polarity correct, and it's not going to be firing from the current flowing from the base to the emitter, only from current flowing from emitter to base. 12 volt peak to peak with no offset, which means it's only going to be getting 6 volts. As we're seeing, our emitter base junction breakdown voltage is 15, so we're not even close to it. Going to hook up our signal generator now, like so, and switch it on, and as you can see, a nice bright LED. So that LED, like it was in our first test, I still have the 1k ohm resistor going across it as well, to keep it all even, and to keep it how it is on our dual phase circuit, and that LED is showing you the current flowing back in the opposite direction of your dual phase circuit, and the transistor switches off via junction capacitance between emitter and base. So it's not just a minute amount, there is enough there to get that little LED from the garden light going quite rightly. And this only happens if you have a 2:1 turn ratio or higher, 1 being L1 and the 2 being L2. So 2 turns for every turn on that, 3 turns, 4 turns for every turn. Anything above 2:1 turn ratio on L2 to L1, you're going to get a current flow back out of the base via this junction capacitance in your transistor, because the LED will only clamp the voltage, and whatever that LED clamps the voltage at, somewhere around 3.5, 4.5 volts, if you have a 2:1 turn ratio, you're going to see 7 to 9 volts on L2 when that transistor switches off. That is in series with L1, the LED, and look where it goes, straight back into the emitter. And we know that current can continue to flow out of the base across that 1k ohm resistor because it's doing it right now. So there you go. It's not a very large amount compared to what L1 is putting out. Nonetheless, it is there, and in this case right here, as you can see, with the voltage we are applying, that is junction capacitance between emitter and base that is carrying that current, or causing that current to flow through. Like I said, I'm not going to get into capacitor current flows and all that crap. At the end of the day, can it flow through a capacitor? Well, obviously, because it's doing it right there, but it is not via the way of electrons. Okay, so that's it. Like I said, this is just in relation to our dual phase circuit experimenting that we are doing, and some are saying that capacitance across that junction is that small, it won't do diddly squat, but that looks like it's doing a little more than diddly squat to me. Even down as small as this tiny little thing here, you've seen how that run the LED across the 1 ohm resistor. So there you go. Right guys, thanks for watching. I hope this helps out a little bit. Every experiment we do towards learning what's going on, hey, all good, hey? Right, we'll see you next video. Cheers from me. Okay, I'm back. You know what I forgot to do? Put the scope on, let you have a look. There it is, the yellow traces across our LED and 1k ohm resistor. 4.4 and minimum voltage 5.4. Oddly enough, looking at the scope now, that's really no more than that tiny little diode there, which is really quite good. A transistor that can carry 15 amps of current and have such a low value, a value that is about the same as that tiny little diode there. But anyway, it's going strong and it's there. Alright guys, like I said, we'll see you next video.